In a previous lecture, we worked out a matrix for n hat dotted into the spin operator. So basically, what is it when what do you get if you take the dot product of our directional vector n and with the spin operator n for all three components x, y, and z? And what we came up with was this matrix h bar over 2 cosine theta sine theta e to the minus I phi sine theta e to the positive I phi minus cosine theta. So now let's see if we can approach this not from the spin, but think of it spin as an angular momentum or a rotation of the spin orientation in some like Cartesian coordinate system, let's say. So if we start with a rotation operator, we'll call it U. We're rotating about some finite angle theta. We would then write this as e to the minus I, that theta, which is a vector, dotted into the spin, divided by h bar. Now, since the spin is h bar over 2 times the Pauli matrix, we can rewrite this transformation as e to the minus I theta dotted into the spin, no, not spin, sorry, that was the whole point, dotted into the Pauli matrix divided by 2. Okay, so now what we can do is we can expand this, so we can make a Taylor expansion of minus I theta over 2 to the power n, 1 over n factorial, and then the I'm sorry. Let's go back. Before we expand it, let's group together the terms in the expression. Sorry, that e to the minus I theta over 2, the theta unit vector, dotted into the Pauli matrix. Now we can do a Taylor expansion of the index n. So minus I theta over 2 to the power n, 1 over n factorial, theta hat dotted into the spin to the power n. So if I now work this out, I get the identity plus minus I theta over 2 theta hat dot the spin matrix plus 1 over 2 factorial minus I theta over 2 squared I plus 1 over 3 factorial minus I theta over 2 the third power theta dot sigma to the third power dot dot dot. Now, in the even terms, I put the identity because we had that one property of the Pauli matrices that n dot sigma squared is equal to the identity. Okay, so therefore I can group terms, and I can come up with the cosine theta over 2 times the identity minus I sine theta over 2 times theta hat dot sigma. Okay, So it's great. So now we've got cosine and a sine term. And well, what is this theta hat dot into sigma? Well, if we think about it, say we're going to rotate into the z direction. So here is n hat, here is the z direction, and we're going to do this rotation around the cross product of those two vectors. So basically I'm creating an orthogonal basis by taking the direction vector, the z direction together, this angle theta at which I do my rotation about the axis which is perpendicular to that plane. So therefore, the theta vector is theta times the unit vector theta, which is equal to theta times my definition of that unit vector is basically what I get, basically the definition of the vector perpendicular to the plane of n and k. Okay, so if I work this out, k crossed into n is equal to I, j, k. The k, z direction is just 0, 0, 1, and the n is nx, ny, and z, which is equal to minus ny in the x direction plus nx in the j direction. The magnitude of k crossed into n is equal to nx squared plus ny squared to the 1/2 power, which is equal to sine theta cosine phi squared plus sine theta sine phi quantity squared. Take the square root of that. Okay, if I factor out sine squared theta, I have cosine squared plus sine, so cosine phi. So I get sine squared theta times sine squared phi plus cosine squared phi, square root of all that, which is basically gives me sine theta. So I have to divide by a sine theta. So therefore, k crossed into n divided by the magnitude is minus ny I plus nxj divided by the sine of theta, which is equal to minus sine theta sine phi plus sine theta cosine phi which is basically minus sine phi in the x direction plus cosine phi in the j direction. And so now, if I put this all together, then u, my operator, which is causing the rotation, is going to be the identity times the cosine. So cosine theta divided by 2, 0, 0, cosine theta divided by 2, minus I times the sine of theta over 2 times that what we have written above. That sine minus sine phi times I plus cosine phi times j. So basically that works out to be, if I work it out, 0 minus sine phi sine phi 0. So that is the nx plus 0 minus I cosine phi cosine phi 0. So that's for ny. So all that together. So if I pull this together into one big matrix, I should have cosine theta over 2, and then minus sine theta over 2 cosine phi minus I sine phi. And then down here I have positive sine theta over 2 cosine phi plus I sine phi, and then cosine theta over 2. Okay, so if I use, write out that Euler equation, then I get cosine theta over 2 minus sine theta over 2 e to the minus I phi, positive sine theta over 2 e to the I phi cosine theta over 2, which is the form that we got before by using by solving the n dot s, where we already had a predefined definition of s. So in this case, we get the exact same form, except instead of theta, we have theta over 2. So basically, I'll leave it up to the students to reason through why do we have the exact same functional form by using a rotational argument, except that the argument now for the sines and the cosines of theta have a theta over 2 angle instead of just having a theta angle.